Okay, this is a fun example, but if you haven't seen circuit diagrams before, I need to give you a quick tutorial on that. This thing here is an AND gate, and this thing here is an OR gate, and this thing here is a NOT. Sometimes you see it as just a circle. Okay, so this is NOT. It turns true into false and false into true. True is represented by a 1. False is represented by a 0. And so the way these things work in the physical world is that we will put a label on these guys like A, B, C, and then we can set these guys to be true or false, and we read the table, we read the direction in this direction. We bring signals in from the left usually, and we push them out to the right, at least the way this is arranged here. So there's 8 possible starting points, and let me just make one up and show you how we can trace it. Like if this is 0, 1, 0, that means false, true, false. Is this true? This is false and true. Are they both true? No. So we put a 0 there. And then this is a NOT gate, so whatever it is, it flips it. If it's true, it's false. If it's false, it's true. So right when that signal gets right here in the crack here, it turns into a 1. All right, and so there's a false and a true coming into an OR gate, and that's true. So that result is true, and maybe I label this D, maybe I label this intermediate step E, and that's how I'm going to label my diagram. Okay, and so I'll just do another example in a different color in case you haven't seen these before. Okay, so let's say I put a true here, a false here, and I'll flip all of them, I guess. It's still not ANDed. Like if both of these are 1, this would be a 1 coming out. But if there's any other combination, it's still going to be a 0. That's still going to be a 1. This is now flipped, but this result is still a 1 because if it's true or true, they're both true, so it's still a 1. Okay, so there's 8 different possibilities that could happen, and one of the things I love about this example, just wipe the screen there. One of the things I love is that in real life, the information flows in the way you would expect, the way the electrons flow through the circuit. Okay, but the way it flows in the sheaf is entirely different. You basically start out in here and you push information outwards. It's very crazy. Okay, let me show you. So this is the self-same structure we were just looking at, but now it's written as a sheaf. And you can make that sheaf symbol anything you want, so I made it a happy face. Okay, so the first thing, remember we said a sheaf has to have sets. So this set, this happy face just means 0 or 1. It means true or false. The set is just a true or a false, and those are the only admissible things you can put on those cells. But some of the cells contain a Cartesian product of 2 happy faces. So we write happy face squared, and all that means is you have a pair of zeros and ones. You either have 0, 0, 0, 1, 1, 0, or 1, 1. So you have a pair going on, and that's great. Okay, so what do we do? So we can start from 2 locations. Again, it's not really intuitive necessarily, but you have to kind of look at it for a while and let it simmer in your brain, because normally, like I said, you should think you're going from left to right. That's the way the electrons actually move. But that is not the way the flow of information is going to work on this sheaf. The sheaf has to kind of go from the area that has more information and propagate outwards to places with less information, if you want to think of it that way. Okay, so this happy face is actually containing one of these 4 things, this happy face squared, and this happy face squared has one of these 4 things. Now, what are these projections? PR means projection. So I have, if I say PR1, that means I take a projection of component 1, and PR2 is the projection of component 2. That's really, it's just switching. It's just saying select one of these 2 items out of the ordered pair. The AND function does what you would think. It turns into 1 if both inputs are 1, and the OR turns into a 1 if either or both is a 1. Okay, so what does this bar mean? It actually negates the whole thing. So this, from this state N2, this cell N2 goes to cell E. If it looks at the first component, but it flips. This is actually the NOT gate. We're putting the NOT gate in there. Okay, so this is not the only way this could have been drawn, but this is one of the simpler ways this could be drawn. And so here's the actual inputs, A, B, and C, and you notice the arrows are not coming from the actual inputs. The arrows are going to the actual inputs, but there's also an arrow going to the actual output. So this is actually essentially the OR gate, and this is essentially the AND gate. And what it's doing is it's asking you to consider consistency rather than causation. And so it flips everything on its head, and you have to think differently about how the data are flowing through. Hope this diagram makes sense. Hope you can stare at it and make sense out of it. Let's go ahead and look at the code. Oh, wait, one more thing before I show you the code. Okay, I went ahead and did this little spreadsheet to show all the different possibilities. I apologize that this crazy code, when I convert numbers to text, it prepends as 0. That's crazy, but anyway, so 0 means 0, 1 means 1, and 0, 1 is just another way of writing the number 1. So sorry about that, but I just wanted to make sure I didn't make any clerical errors, and then I just repeated A, B, C, D, E in the order in which they are alphabetically. But this is just so I have 8 examples of consistent labeling on that particular diagram. So I'm going to be referring to this table as I play with the code. Okay, here is the code, and before I forget to tell you, here's the long-awaited promise. This is how you control the max iterations. The default is 100, and so if you just simply uncomment this, nothing will happen. But I'll leave it commented until I want to change it. Okay, so I'm going to go ahead and run this code, and one thing I did is I ran this code where, okay, so A, B, and C are the ones you actually get to choose, and then for my bogus data assignment, I just put 0.5s on everything. I don't consider it a win if it lands on 0.5. I'm going to allow, like if I get to 0.8 or 0.9, I'm going to assume that rounds to 1, but if the thing lands on like 0.1 or 0.2, that can round to 0. But 0.5 is right in the middle, and it doesn't really round anywhere. I mean, you can argue that it does, but like in this case, it doesn't make any sense for it to land on 1/2. Okay, so we're going to see if we can get a consistent read out of this. And so remember, ABC is 1, 1, 0. Okay, if ABC is 1, 1, 0, we can look over here to see where that is. ABC is 1, 1, 0, so we're looking at this line of code, and D should be 0, and it is. E should be 1, and it is. What does N1 look like? It should be 2 1s, and it is. And N2 should be 2 0s, and it is. Great. So we could pick another one and try it. I'm going to pick 0, 0, 0, 0. So, I'm sorry, 3 zeros. I'm going to try starting with 3 zeros. I'm going to save this. And let's see, what does it look like? I should get zeros, except D should be a 1. Let's see, E should be a 0, and 1 should both be zeros, that's correct, and 2, I should get a 1 and then a 0, and that's what I get. And notice the consistency radius is very, very low. It started out like not that very high, but you know, in this example, maybe 1 is high in this environment. You know, like maybe that means something different than it does in the other example, because distances are different here. So a little trick, a little sneaky trick, it actually is using what as the norm. It's 2, because I'm not actually using booleans, I'm not using trues and falses, I'm using zeros and ones. And so The reason for doing this is actually to allow the optimizer to slide from 0 to 1, and that's a pretty common trick. You've probably seen that before in other statistical applications where you're doing some kind of logistic regression or something, and you're pretending that you can go smoothly between 0 and 1 when you really can't, but you have to pretend to, or the optimizer won't work. Same deal here. I guess I didn't show you the horrible plot. I can go ahead and do that. PLT show. Isn't that gross? Anyway, well, it's not that bad. And if you run this code again, this is the annoying part. If you run it again, you'll get a different picture. But anyway, I'm going to go ahead and change the max iterations here so we see how bad it is if we go down to like 5. I'm just making that up. That's pretty nasty to do that to the optimizer, but let's see how well we do if we only allow it to run 5 times. So let's see, D should be 1, E should be 0. I'm actually impressed. I didn't know this would work this well. Okay, so yeah, I'm kind of impressed with that. So have fun with these and play with these examples. See if you can come up with your own examples. Yeah, I guess that's it for that example, and let me know if you have any questions.